Welcome everyone. We are going to be doing ionic and covalent characteristics today. This is going to be related to the lab that we're doing in class, looking at different substances and testing for their melting point, their solubility, and their conductivity. So this is all directly tied to that, but also gives an introduction to each of the different types of bonds, ionic and covalent. So as we get started, the first thing that we want to make sure that we take a look at is kind of what's the reason behind chemical bonding. And so what I need you guys to understand is that atoms bond in order to fill their outermost energy level. And if you guys remember from the last unit, we called this where their valence electrons live, so valence shell. And remember, that's where the valence electrons live. Okay, so when we're looking at these valence electrons, remember we talked about the valence electrons are the ones that matter because they are the ones that are involved in bonding. And so anytime we're talking about bonds between two different atoms and then taking that further into chemical reactions, it's really the valence electrons that we're looking at every single time. So what's going on in this outermost energy level is really the most important activity that we look at in the atom. So as a result, the act of bonding increases the stability of the atoms in the compound. So when atoms choose to bond, they are doing so to fill their outermost energy level, so to fill their valence level. And remember that our magic number is 8 based on the noble gases. So noble gases are happy because they have 8 valence electrons, and so they don't have any needs to fill. Their outermost shell is completely full and they don't need any others. So that is the state of stability that everybody else is looking for. So the closer you are to having 8 valence electrons, the more you want those electrons to complete that outermost shell. The first type of compound that we're going to talk about are our ionic compounds. And in an ionic compound, we're going to be looking at a metal and a nonmetal bonded together. And so when we have a metal and a nonmetal, we need to remember where those are found. Metals are found on the left side of the periodic table, whereas nonmetals are found on the right side of the periodic table. And we need to remember that our stair step is the dividing line between those. So these compounds are created by actually transferring electrons. And what we mean by transferring is completely changing ownership. So they actually give electrons away, or they take electrons from another atom, and those electrons now belong to somebody else than who they belong to originally. So we are not changing the identity of the atom because nothing is changing with protons, but we now are talking about atoms that are no longer neutral. So up until now, we've been saying that everything is neutral, all we're dealing with is neutral for now, but starting today, that's not going to be true anymore. Because in this situation, when you give away electrons or take electrons from somebody else, then either your protons are left winning or your electrons are left winning, meaning there's more of one or the other. Now again, we cannot ever change our protons, so we know that the only way to make that change is to give or take electrons away. So we'll talk about what that looks like in just a minute. So this loss or gain of an electron creates something called an ion. So again, we're no longer talking about neutral atoms, we're talking only about ions. And this, the definition of an ion, is just a charged atom. So again, it's not neutral, it now has a charge. So we have two different kinds of charges. We have a positive charge and a negative charge. Positive charges, positively charged atoms are called cations. It's not cation, it's cation. And negatively charged atoms are now called anions. And the easiest way to remember this is that the T in cation looks like a plus sign. And so that's how you remember that one's positive, so the other one must be negative. So when we look at how this happens with an atom, we look at, for example, we're going to look at magnesium. And then I draw magnesium. There's its nucleus, first energy level, second energy level, third energy level. Magnesium has 12 electrons, so here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we know that magnesium is in group 2. It has 2 valence electrons. It ends its electron configuration in the S2 spot. So that makes sense that these valence electrons are the outermost ones and that there's only 2 of them. So the question we have to ask ourselves, is it easier? Remember, our magic number is 8. So is it easier to get rid of 2 or to find 6 somewhere? And the answer should be that it's easier to get rid of 2. So when we get rid of those 2 valence electrons, what that reveals below is a completely full valence shell. Because now the second energy level is our outermost energy level, and the second energy level has 8 valence electrons. So we've reached our happy number. So we write that as a 2 in that 2 electrons were transferred, and we decrease the number of electrons, so now the protons are winning. So that gives it a plus charge overall. Again, we don't change protons, we just change electrons. But in this case, we decrease the number of electrons, so the protons are winning. On the other side of that, if we look at the atom for oxygen, here's oxygen's nucleus. Oxygen has 8 electrons total. It's got 2 in its first energy level, and then it has 6 in its outermost energy level. So 6 is not 8, but we still want 8. So is it easier, again, we have to ask ourselves the question, is it easier to get rid of 6 electrons or find 2 electrons somewhere? And in this case, it's easier to gain 2. So in this case, I gained 2, so I've added extra electrons than what I had before, so my electrons are winning. So the number refers to how many electrons change hands, and the sign refers to who's winning in the end. So over here with magnesium, we took away electrons, so that left protons winning. It's opposite math. I end up with a plus charge when I subtract electrons. On oxygen, I added electrons, so that gives me extra electrons. They are now winning, so I end up with a negative charge. Again, it's opposite math. I added electrons, so I end up with a negative sign. So each of these can be summed up with the loss of electrons revealing that completed lower energy level. That's what makes a cation. And the gain of electrons completes the existing energy level that's already on the outside. That's what makes an anion. This act creates opposite charges, and we'll talk more about that in the next lecture, creates opposite charges on each of the atoms, and that creates, we know that opposite charges are attracted to each other. So this creates a bond of attraction that actually is quite strong. Even though they're not physically attached to each other, it's really, really a strong bond. So circling back to what we experienced in the lab, our ionic substances exhibit a high melting point, meaning it is very difficult for them to melt. We have to get it really, really, really hot for them to melt. So because those very strong bonds require a lot of energy to break between them, so that force of attraction is so strong between them, we have to put in a ton of energy to break those bonds and cause it to melt. We're not talking about bonds between, we're not talking about bonds between like different molecules or anything like that. That's a different situation. But we still have that force of attraction that we have to overcome to get it to melt into its liquid form and be flexible. They're also soluble in water, and this has to do with the fact that they actually share a similar property with water. We're going to talk specifically about that later in the unit. But the phrase that I would like you to remember with this is that like dissolves like. So because water and ionic substances share that special property together, they're soluble with each other. So like dissolves like. So if you were to put it in a substance that it did not share that property with, then it would not dissolve because you would have two different situations and you don't have that like dissolves like scenario. Lastly, they exhibit a high conductivity, and this is specifically in some kind of liquid state. So it either has to be in solution or melted. And that's because their solubility, because they're soluble in water, it allows each ion to conduct electricity. We need moving electrons in order to conduct electricity. We have that here, so it's good to go. Next are our molecular compounds, and this is the same as covalent, and this will go a little bit quicker. It's a nonmetal and a nonmetal. They create compounds by sharing electrons instead of giving or taking. Everybody just kind of claims the same set of electrons. And so because they're shared between atoms, you can have two or more atoms that are bonded together via this sharing. And what happens is the electrons actually circulate all the way through all of the atoms that are bonded together, kind of like a rotation. And it allows them to completely fill the outermost energy level for each atom, even though that doesn't always happen simultaneously for all of them, because they're circulating through all of them together. This is an actual physical bond called a covalent bond. So covalent and molecular need to go together in your head. And so these elements are actually physically attached to each other. The funny thing about that is that even though they're physically attached, they're not as strong as ionic bonds. That force of attraction in the ionic bond is stronger than what we experience with this physical attachment in covalent bonds. Covalent substances are basically the opposite of ionic. So they exhibit a low melting point, so it's really easy to melt them. And this is because those bonds are weaker. So we don't have to put as much energy into it to get them to melt. They're also insoluble in water. So again, we said like dissolves like. So what that tells us is that these covalent bonds are not like water. So they're insoluble. So they do not share that property with water that ionic bonds do. And again, we'll talk specifically about that property later in the unit. And then lastly, they do exhibit, because they're not soluble, they exhibit low conductivity. We don't have these electrons flowing around in open space. They're rotating between each atom. And so we have a low conductivity as a result. Their low solubility reflects that we don't have these charged particles moving around and that have the ability to move around. And so they're not able to carry a charge when we put one in there. So that's the basic summary of ionic and covalent bonds. We will still touch on metallic as well, but that covers the basics for ionic and covalent, which we'll spend most of our time on, and then also gives you the information that you need to categorize your substances from the lab. Hope you guys have a great day. We'll talk to you later.